Okay, so our objective today is to describe what the Intel manual says about canonical addressing. So we're on page 72 here. Okay, to start, let's go ahead and define canonical. I think the second definition here is probably the one that applies to us. This means conforming to a general rule or accepted procedure. So in 64-bit mode, we're going to look at a certain way of addressing things. And how do we know we're in 64-bit mode? Well, it will say right here. So let me give you the whole sentence. In 64-bit mode, an address is considered to be in canonical form if address bits 63 to the most significant implemented bit by this microarchitecture is set to either all ones or all zeros. If we go back up here, I noticed 63. And Intel uses this little Indian style of doing things, so keep that in mind. Now let me read this next sentence that I'm calling worthless. You may or may not agree with me. It says Intel 64 architecture defines a 64-bit linear address. Okay, thank you for that. Now here is a pretty short sentence for the Intel manual. It says implementations can support less. But then it wouldn't be canonical addressing, would it? Well, they go on to say that the first implementation of IA32 processors with Intel 64 architecture supports a 48-bit linear address. Well, they go on to say that this means a canonical address must have bits 63 through 48 set, either to all zeros or all ones, depending on whether bit 47 is a 0 or 1. Okay, so this is not arbitrary. So it says although implementations may not use all 64 bits of the linear address, they should check bit 63 through the most significant implemented bit to see if the address is in canonical form. If a linear memory reference is not in canonical form, the implementation should generate an exception. Alright, so just give us this error message that we're not in canonical form and we're good. In most cases, a general protection exception, that's what this stands for, I guess, is generated. However, in the case of explicit or implied stack references, a stack fault through the stack segment is generated. Instructions that have implied stack references by default use the SS segment register. So a good question to ask, what uses the SS register? The answer is stack references do, or instructions that have stack references in them, that is. These instructions are using the SS segment register. Now these include push and pop related instructions and instructions using the stack pointer and the base pointer in a 64-bit system. Remember, anytime you see R, we're talking 64 bits. Or a 64-bit register, that is. Now in these cases, the canonical fault is number SS. Now if an instruction uses base registers RSP, RBP, and uses a segment override prefix to specify a non-SS segment, a canonical fault generates a general protection exception instead of this segment register, or should I say a change in the segment register number. Now in 64-bit mode, only FS and GS segment overrides are applicable in this situation. Other segment override prefixes CS, DS, ES, and SS are ignored. Now note that this also means that an SS segment override applied to a non-stack register reference is ignored. Such a sequence still produces a general protection error or exception for a canonical fault. So that second to last sentence was really difficult. Let's turn it into a question. When is a SS segment override ignored? The answer is when this override is applied to a non-stack register reference. So, I mean, this is rough. My explanation of these things are really rough right now. But if we're starting at ground zero here, we're just getting used to the language. Let's jump over to Stack Exchange to help us with the concepts that they were throwing at us in those last paragraphs. So here on Stack Overflow, the person asks questions like, they say they know what these are, but what are the following registers intended to be used for? So that's that FS and GS we saw. So let's take this answer and also create a bunch more questions so we could walk away from the canonical addressing part of the Intel manual with more confidence. So the person first starts by saying that there is an intention to the registers, but then there is the reality of what Windows and Linux did with these registers. He says that the original intention behind the segment register was to allow a program to access many different large segments of memory that were intended to be independent and part of persistent virtual store. The idea was taken from the 1966 multics operating system that treated files as simply addressable memory segments. How did multics treat addressable memory segments? I really like the answer to that. It treated these as files. Or should I say it the other way around? Should I say, how did multics treat files? There you go. And the answer is, they treated files as simply addressable memory segments. Now they go on to say our current 2010 operating systems are a giant step backwards, which is why they are called Unix. You can only address your process space's single segment, giving a so-called flat address space. So yep, we are reading about flat address space in this part of the manual. The segment registers on the 8632 machine can still be used for real segment registers, but nobody has bothered. And he's specifically calling out Andy Grove, former Intel president here. So Andy has not bothered. And he apparently discovered something really good. That money and energy was being wasted. So to carry on here, AMD, in going to 64 bits, decided they didn't care if they eliminated multics' choice. And then the guy says it could be that AMD had no clue about multics. But what AMD did is they disabled the general capability of segment registers in 64-bit mode. There was still a need for threads to access thread local store, and each thread needed a pointer. So this part is a little crazy, but I mean I do understand the need or concept of a pointer. And I think in this video you guys do too, in terms of like a pointer is a value that is an address. It's like pointing to that address that is the value. Oh, I hope I did a good job explaining that. Maybe if I show you like how typically we can create a variable and assign it some sort of like a value, like it could be a word or it could be like even just a straight up number. It's my understanding that essentially these are pointers. So it's saying here at this address, whatever that, there we go. So whatever that address is, at that address, you could have the value of the word or whatever. That's essentially the same thing as doing this, having a variable and assigning it this value. Okay, so somewhere in the immediately accessible thread state, for example in the registers, to the thread local store or to thread local store. Gosh, I don't know what that means. But this is the money part, and I guess I'm going to keep this in the video just so you know that there are things that you'll read and you don't know. But that's not the point of these kind of videos. The point is we are learning some stuff together rather than you just being alone trying to learn on your own. So to keep reading, it says, since Windows and Linux both use FS and GS for this purpose of pointers, right, of having a 64-bit pointer, that's what Windows and Linux is using these two segments for. If we go up here, I like that he called this file segment because that kind of makes sense, especially in the context of what we're reading in the manual. Or no, it didn't say it in the manual, it said it at the top of the Stack Exchange. The idea was taken right here where it says that the idea was taken from multics and that they treated files as simply addressable memory segments. So to have a file, to open a file, you go to this address, and that entire segment is the file. Okay, so that's what I'm saying kind of makes sense in the context of FS standing for file segment, the value of the address where the file begins. Well, I like this answer here where it says the registers FS and GS are segment registers. They have no processor-defined purpose. So essentially the FS and GS, they could stand for anything. DS would remain segment though. But whatever this segment is identifying is, you know, up to the operating system. In Windows 64-bit, the GS register is used to point to operating system-defined structures. FS and GS are commonly used by operating system kernels to access thread-specific memory. In Windows, the GS register is used to manage thread-specific memory. Now, the Linux kernel uses GS to access CPU-specific memory. So maybe let's just settle on which two registers' purpose depend on the OS. And so your answer is the FS and the GS registers completely depend on the operating system. And I like this answer because they're actually using some assembly code to show you how that register would be utilized. But I'm going to have a whole nother video series on assembly code because that cannot be easily explained. So that's canonical addressing. I think it is one of the most confusing parts of the Intel manual so far. Maybe if we answer some of these questions we could feel more comfortable with it, but this will be one of those that I think we come back to as we read more and learn more in this Intel manual.